Welcome back to the Deep Dive. It is Saturday, February 7th, 2026. And if you're listening, well, congratulations are in order. You have officially survived the theory-heavy start of CS330.
You made it through the diagrams.
I made it through the diagrams.
Yeah.
I've drawn the state transitions, and I've definitely had a nightmare or two about, getting stuck in an infinite loop in a finite automaton. But the vibe changes today.
It really does. This is a pivot. We're moving from the abstract, all the circles and arrows on a whiteboard, to something, really concrete. We're looking at the actual tools that turn those concepts into code that runs.
Yeah, we're digging into the Class 8 notes, specifically make and flex.
Right. And if you think about that compiler stages diagram, figure 2.2 in the notes, we've been stuck at the very, very beginning, the character stream.
Just a stream of letters.
Exactly. Today, we are officially stepping into that first box, the one labeled scanner. This is where the text starts to become tokens.
Okay, but before we get to the scanner, the notes start with the builder.make. And I have to ask, for a simple hello world, I just type GCC and I'm done. Why do we need a whole separate tool for this?
That's a great question. And it's really all about scale. For one file, you're right, you don't need it. But the compiler you're about to build, it's not one file, it's dozens. You've got source files, header files.
All interacting with each other.
All interacting. So imagine you have a project with 50 files. You change one single line of code in just one of those files. Do you really want to recompile all 50?
No, absolutely not. That sounds like a huge waste of time.
It is. So Make is like a smart project manager. Its whole job is to figure out the absolute minimum amount of work it needs to do to bring your project up to date.
So how does it know what up to date even means? Is it like reading the files?
Oh, no, that would be way too slow. It's actually much simpler and kind of clever. It just looks at the file timestamp.
The last modified time.
Yeah, exactly. It compares the source file, say main.c, to its output, main.o. If the source file is newer than the object file.
It assumes you changed it.
Right, and it rebuilds. If the object file is newer, make just says, nope, nothing to do here, and it stops.
That's very efficient. Yeah. But what if I change a header file? One that's included in like 10 different C files.
And that's the magic of the dependency tree. You tell Make about that. In your configuration file, you list the header as a dependency.
So it knows.
It knows. It sees the header file is new, and it follows the chain to recompile everything that depends on it.
Okay, so this configuration file, that's the make file.
That's the make file. And the syntax, well, it's a bit rigid, but it's logical. It's all built around these things called targets. A target is just the file you want to build.
The slides show a specific structure. It's target, a colon, and then dependencies.
Right. And then on the very next line, and this is the part that gets everyone, you indent with a tab character.
A literal tab.
Yeah.
Not 4 spaces.
A literal tab. You use spaces, it will break. It's a classic Make gotcha. After that tab, you just write the shell command you want to run, like cc-c hello.c.
So it's basically a recipe. To make this thing, you need these ingredients, and you follow this instruction.
It's a perfect analogy. And the notes also mention variables, which are super useful. You can define CC to be Clang at the top, and then just use ECC everywhere.
So you only have to change it in one place if you switch compilers.
Exactly. Don't repeat yourself. It's just good practice.
And what about this clean target? The notes say it's idiomatic.
Right. Make clean. It's like the reset button. Its job is just to run ARM and delete all the files that the compiler generated, all the object files, the final executable.
So you're left with just the code you wrote.
Just the human-authored code. It's really satisfying to run, and it's useful if you think the build is messed up and you just want to start fresh.
Okay, so Make handles the whole build process. But the real core of this lecture and the upcoming lab is the tool that generates our scanner. Let's talk about Flex.
Flex. The fast lexical analyzer generator. This is the moment where the theory connects. You asked why we spent weeks drawing all those circles and arrows for DFAs.
Yeah, I was wondering when we were going to get away from the whiteboard.
Well, this is it. We are not going to hand code those DFAs in C.
I was hoping you'd say that.
You could, but it would be a nightmare. Imagine a giant switch statement with hundreds of cases trying to track state. It's just so easy to make a mistake.
So Flex automates that part.
It completely automates it. You give it a file with regular expressions, your patterns, and Flex writes the C code for you. It generates a perfect, efficient DFA implementation.
So it's like a compiler for a piece of our compiler.
That's a great way to think about it. It reads your input file, which by convention ends in TOCL, and it spits out a C file, almost always named lex.yy.c.
And that file is the scanner.
That file is the scanner, ready to be compiled.
Okay, let's look at that .l file. The notes show this structure with the % symbols. It looks a little weird if you're used to just C.
It is its own special format. It's broken into 3 distinct sections, and those double % signs are the delimiters.
So section 1, the top part.
That's your declarations and definitions. Any C code here just gets copied verbatim to the top of the output file. So your hashtag includes statements, global variables, things like that.
Then we hit the first %, the middle section.
That's the main event, the rules. This is a 2-column layout. On the left, you put a regular expression. On the right, you put the C code you want to run when that expression matches.
Pattern on the left, action on the right. Simple enough.
Yep. And then after the second %, the third section is just user code. Anything here gets tacked on to the very end of the C file. This is usually where you'd put your main function or other helper functions.
Okay, so Flex generates this C file. We compile it with make. How does our program actually use the scanner? What's the function we call?
The function is mylex. Flex writes it for you. Your main program, or later your parser, will just call lilex over and over again in a loop.
And each time you call it, what happens?
It consumes characters from the input stream, finds the next longest match for one of your patterns.
And then it runs the action code for that pattern.
Exactly. And then it returns a value.
What does it return? This seems important.
It returns an integer. That integer is the token's ID. So in a compiler, you define number to be, say, 258 and ADD to be 259. When Alex sees a plus sign, it returns 259.
And it keeps doing this until it runs out of file.
Yes. When it hits the end of the input, Alex returns 0. That's how your loop knows to stop. The classic pattern is while token malex, process the token.
Okay, here's the question that really got me when I was reading the notes. If Yelex finds a number and just returns the integer 258, how do I know if the number was 5 or 500?
Ah, yes, the value problem. This is the most critical concept to get right. The return value from LXX tells you the type of the token. It's a number.
But not the value itself.
Correct. For the value, you have to look at a special global variable called yilval.
That's like a side channel for data.
Exactly. It's the payload. Let's look at the calcskeleton.l example. It has a rule for a sequence of digits, 0-9 plus.
Right, that matches one or more digits.
So when Flex matches that pattern, it takes the actual text it found, say, the string 42, and it stores it in another special variable called itext.
So itext is a string that holds 42.
Yes, but we need an integer, not a string. So in the action code on the right side, you'll see the line yelval equals a toy itext.
It converts the string to an integer and stuffs it into yolval.
Exactly. And then after doing that, it returns the token ID, number. So the caller gets the number token, and it knows it can now look in yolval to find the actual value, 42.
It's a two-step communication. The return value is the what, and yolval is the which.
Perfect. If you miss that, your calculator can't calculate anything.
There's another really clever thing in that calculator example. The rule for white space, yolvel, its action is empty. It's just a comment.
And crucially, there is no return statement in that action.
So what happens? Yolex matches the space, runs the empty action, and then what? Does it just stop?
No, it just keeps going. This is a special behavior in Ilex. If an action doesn't explicitly return a value, Ilex just resets and immediately starts looking for the next token.
So it just eats the white space.
It eats it and forgets about it. That's how compilers so easily ignore white space. You don't write any logic to skip it. You just write a rule to match it and do nothing.
That is really elegant. And then there's the last rule, the single dot.
Catch-all, the error handler.
Right. Since Flex tries rules from the top down, that dot will only ever match if nothing else did.
Exactly. It's your safety net. If the user types a character you don't have a rule for, like an ampersand, the dot catches it. The action in the example just prints a warning. Without it, your scanner might just crash.
Okay, so this all leads directly into Lab 2.
It does. This is the immediate application. The notes are clear. Open your terminal, get into your lab work directory, and run git pull.
Do not forget git pull. I can just hear the panicked emails now. Where's the Lab 2 directory?
It's there. You just have to pull it down. And inside, you'll find a make file, flex files, C files. Your job is to modify them and add to them.
The due date on the syllabus is Monday, February 16th, which gives us a little over a week.
It does, but look at the rest of that week. There's an LLM roundtable on Friday the 13th and a journal entry due on Sunday the 15th. I'd really recommend not leaving this lab until the last minute.
The notes also describe this lab as low risk. What should we take that to mean?
It means it's a chance to learn the mechanics without a huge amount of grading pressure. It's better to get confused about YILVL now on this lab than on the main compiler project where the stakes are much higher.
Because the full B minor compiler is coming up fast.
It is, and this lab is the foundation for it. If you master this loop call YLX, check the token, get the value from YILVL, you'll be in great shape.
So to wrap this all up, we are officially getting our hands dirty.
We are. We've moved from pure theory to the sometimes messy reality of makefiles and generated code.
It really feels like the big theme of this course is coming into focus. We're not just writing code anymore. We're writing code that writes code.
It's very meta, isn't it? And that's maybe the provocative thought to leave you with. Think about the layers here. You are writing a flex file, which is a form of code.
To generate a C file.
Which is code. That gets compiled into machine code, which processes B minor source files, which are also code.
To eventually produce assembly, which is code.
It's code all the way down. But what's interesting is where the human intent lies. You're no longer telling the computer how to find a number step by step. You're just describing what a number is with a regex. You're the architect, not the bricklayer.
That's a powerful way to think about it.
It is. So your mission is clear.
All right, learner. Get that git pull done. Dive into the Lab 2 Flex introduction directory.
And check the syllabus for the team and individual parts, and really try to get that makefile working for the extra credit. It's great practice. Debugging a build process is a skill for life.
Wise words. Thanks for tuning in to this deep dive. Go build a scanner, and we will see you further down the pipeline.
Happy coding!